Day 6 Hack Night. This is a continuation of our series that we're doing in May, the Spicy Data Collection Challenge. So in the first week's episode, we covered how to connect to a variety of EEG devices using a couple of different platforms. So there's a demo for how to connect to a Muse device on Windows using the Blue Muse functionality. There's a demo of how to connect to the OpenVCI. There's a demo of how to connect to the Mind Monitor app on the smartphone. And there's a demo for how to connect to the Neurosity Notion 2. So that should kind of get you going on how to get connected. But if there's any difficulties, we're happy to help pitch in on Slack. Usually the problems that are encountered on a given platform or a hardware are not that uncommon. So if you're still having any difficulties after the first video, please drop into the NeurotechXF Slack, and we would be very happy to assist with any questions you may have. And I'm sure we could also schedule a sort of hands-on hack night for anyone who's been following along but is having difficulties, so that we can just sort of dedicate that to resolving issues. I think that would be great to share with the community if you're open to sort of having that broadcast. Okay, cool. And this week, we're going to be focusing on, now that the device is connected, how do we actually get data off of it? How do we store that data in a place that we can analyze it later? And how do we do some kind of initial verification to make sure that, you know, it's correct? Like, is there some basic validity checking that we can do so that, you know, we have an idea of, oh yeah, that looks right, or no, that's not quite what I'm expecting. The one thing to keep in mind is that different EEG devices may make some rather different looking traces. And so it would be useful to go through some of those and hopefully give folks an idea of what to expect. All right, so in terms of the first demo, I'll be walking through how to use Muse LSL to collect data off of a Muse device on Windows. And the bridge interface, just like last week, is going to be the Blue Muse that we installed on this OS. So pretty much just a continuation of that. So I'll be sharing my desktop here in a moment. Let's see, I need to close that. Okay. And right, let me get this nonsense out of here. Okay. So let's also share the desktop so that you can see what's going on. Okay, so we're going to do the whole screen. Cool. All right, so if this breaks at any point, please let me know in chat or whatever, because sometimes Jitsi decides to stop updating, but we'll just assume that it's, can you see my screen?
Yes, I can currently see your screen.
All right. Check chat.
I'm also going to turn on the lobby function.
Yeah, it's a great call. Thank you. All right, well, if anybody can't see my screen, please shout in chat. All right, so let's get started with the Blue Muse connection. All right, so step one is turn on the Muse. So we've got the strobing lights. Here, I'll stop sharing just for a moment so you can kind of see. This is a Muse ready to connect, just like last week. So when we've got it powered on like this, I will open up the Blue Muse. Cool. And it is searching for devices. All right, so the Muse just went to a solid light, which is usually a sign that the Blue Muse found it. Yep. And here it is, detected the device. It shows online. Battery is full. Might have charged it right before the call, and it is not currently streaming. So let's get that rolling. Start streaming. Cool. And as we can see, the stream has been generated. We've got our EEG, 4 channels. We've got accelerometer and gyroscope. And these are the sample rates that we're expecting for these. So first part is, let's just make sure that, just like last time, we've got the connection. We can look at the plots and make sure that that's good. Okay, and as you can see, I'm not wearing it, so it looks like the noise pattern for any ambient muse. All right, so let me actually put it on. Cool. And how about some blinks? Hey, all right, we've got data. Cool. So this time, we're going to close the viewer. Now, if you're not familiar with you can always just type MuseLSL, and you'll get some syntax. Obviously, you can find the documentation as well, but this will give you some idea of what you can do with it. So record is going to be what we're doing today. And one of the things I'd like to call your attention to is the duration. In MuseLSL, there is a default recording time of 2 minutes. That's a very reasonable time to record, but it definitely caught me out a few times when I thought that I was doing longer recordings, and they cut off after 2 minutes. So if you need to do a lengthy MuseLSL recording, you want to use that D parameter to kind of provide the time. I haven't used MuseLSL in a while, but the way that I used to do it was I would set the duration to something much longer than I was intending to do as a recording, and I would just come in here and stop the process. I believe it was Control-C, but let's see if we can get this to record successfully. All right, so let me also go to desktop, and I'm going to make a new folder called Muse Data, and we'll record in there. All right, so MuseLSL. So we're using the record syntax right here. And we're going to, -D is going to be, I don't know, 60 seconds. And we're going to keep this nice and short. And we're going to call the file first data. I think this will go into a CSV. Let's see if this works. All right, so I remember MuseLSL having a hard time if it didn't find a marker stream. And I'm pretty sure there's a way to tell it to ignore markers, and I think there's a way to comment it out. But let's see, what exactly are we getting here in the record trace? So it starts recording, it got the time correction, and oh, it's trying to make a direction. All right. Let's see if we can get this to work. Negative. Okay. Well, this is going to be the world's most boring hack night. All right, I'll try to see if I can troubleshoot this in a reasonable time frame, and if I can't, MuseLSL. This is probably my first step to troubleshooting, sadly, which is, yeah. Through the record. All right. I'm gonna cheat a little bit. We have a recorder that we wrote. It's a general purpose LSL recorder. So sadly, this is not going to be a MuseLSL demo, just because I didn't troubleshoot the recording functionality. But we are going to get data, and we are going to look at it. So pardon the fact that this is with All right, so if we do a list command, we can see the streams that are active. So we can see that the gyroscope, EEG, and accelerometer are running. And I'm going to say first data.csv to make life easy. Cool. And the sudden silence is I'm trying to get a few seconds of non-terrible data, but I think that quest is unlikely to complete. All right, we should have some. So I'm going to go ahead and hit Control-C, which writes the files. Cool. So again, sorry for the fact that this is not going to be 100% for what you're doing, but I'll definitely get the Muse LSL functionality going. In the meantime, let's get these in the Muse data folder. Okay, so what you're going to have is going to be equivalent to this EEG file. When Muse LSL records, it's not going to grab the accelerometer and gyroscope, so you're probably not going to have these additional files, but you will get the EEG data, and that should look pretty similar. So what does recorded EEG data look like? Well, in this case, we have the Blue Muse timestamp, and this is generated through something called LSL, and it's in Unix time elapsed epoch. So you can go to Unix epoch converter, and this is a website where if you have something you want to convert, bam, and you can see that this was right here, and of course this is going to be in GMT time. So you can see that this was in fact 2 minutes ago. So yeah, if you run into these weird timestamps, 162 whatever, that's in Unix epoch time. Just Google Unix epoch converter, go in here, and you can get some sense of where it is. If you haven't already memorized what this timestamps convert to. Okay, so what this is showing us is that this is each sample that's coming in, and the Muse is a 256 samples per minute device, or I'm sorry, second. So what you would expect is that each sample is going to be roughly 4 milliseconds apart from each other. So whatever device you're looking at, here we're incrementing from 832 to 836 to 840. So this is probably the millisecond scale right here. And it's incrementing by 4. So the next one should be 844 or so. Hey, and 848. All right. And okay, so here we have some timestamp jittering. We're going to pretend that that didn't happen. But for the most part, it should be sequential, and you should be able to see that the time increment matches the data rate of the device that you're expecting. Okay, so the second thing is we want to look at the voltages and make sure that the voltages look about right. So all of these are averaged to 0 because of the Blue Muse functionality. And so, oh, I'm sorry, they're not averaged to 0. No, they are. Okay, cool. So these are median subtracted. And this is one of several forms that you'll encounter this data with. So basically what that means is whatever the mean is of each electrode gets subtracted, so that it's really giving you the voltage of kind of like that moment in time away from the baseline rolling mean. Okay, so in the 4 electrodes on the Muse are the AF7, AF8, TP9, and TP10. There is, if you look at the Muse device, I think we covered this, but this is AF7, this is AF8, This is TP9, and this is TP10, and this is like the front of the Muse device. So these two are the frontal electrodes. They tend to have lower signal and less voltage. And that's because the reference electrode for the Muse is in the very center of that magnetic strip. So the reference electrode gets subtracted from the two front electrodes. And because it's in a location that's very close, proximity-wise, to the two front electrodes, it means that the signal that it's subtracting is similar to the two front electrodes. So on the Muse, the front electrodes are in a very interesting location, which is great because they get you that frontal spot. On the other hand, because there's no ear clip, because of the form factor, the reference is in the front, so you're going to just get less power on the front electrodes. The rear electrodes will give you more signal and more power because the signal that's being subtracted from this reference is quite different. The distance is larger, it's a different part of the brain, et cetera. So you're going to get stronger amplitudes in general on the rear electrodes. Okay, so this is the front left and the front right. As I mentioned in last week's chat, a lot of the times, because of the fact that this Muse device is rigid, it's going to tend to make really good contact on one electrode in the front. Some people are fortunate and get great contact on both, but some people only ever get one, and there isn't a lot of consistency. So one of the things with the Muse is, you know, I'm often keeping in mind, do I think I'm going to see one good channel or two good channels? Now, looking at the numbers can be, you know, a little bit like, okay, yeah, whatever, I see a bunch of numbers, great. But there's a quick and dirty way that you can do this in Excel or whatever. You can just plot it. Hey, that's what this looks like. So this is good EEG data, right? The parts that, whatever. Here's me talking, explaining the silence. You can see why EEG doesn't like the subject talking, moving, doing anything like that. And then here's me, you know, saying some stuff at the end as I'm cutting off the recording. But you can use this to kind of very, very quickly inspect the data and kind of get a feel for, all right, what do you see in this electrode? Let's take a look at the next one and do the same thing. All right, we're going to check the other front electrode, AF8. Okay, so this one seems to show those three blinks that we were doing at the start, right? There's a little bit more of the activity. And I would say that, on the other hand, look at all this squiggling, right? This is not what we're expecting to see. What we're expecting to see is sort of a nice, small, rhythmic pattern like AF7, right? This one behaves itself. It kind of hangs out until I'm doing something like talking. But this one's all over the place. The voltage is up. It's up 200 microvolts here. It's dipping. It's spiking. Whatever. So even without any way to like inspect this data, I can say, oh look, you know, my AF8 fit is terrible, just like always, and my AF7 fit is fine, just like always. So this is sort of a very quick and dirty way. But if you have some idea, or if you compare the channels, what you're looking for on a Muse device is a smaller range. Let's just delete these, good Lord, of voltage, so that, you know, let's say the oscillations are plus or minus 20, 30 microvolts. That's been my experience of how you can do a good channel. Different devices, different, you know, methods, maybe a little thing, but you can get a sense from how much it's oscillating, whether the connection is good. All right, and we'll take a look at the rear electrodes real quick, just to kind of compare those two. And boom, we're going to plot this. Okay, so TP9, yeah, it's good, but there's a lot of stuff here. On the other hand, maybe that's just what we've got. And let's take a look at TP10. All right, is that worse? Boy, these rear electrodes. So if I was looking at these, I think I prefer TP9 because, yes, there's a lot of noise and activity in both events, but, you know, TP9 at least looks like somewhat clean EEG data. TP10 looks pretty noisy. So this is a very, you know, rough if you're just inspecting somewhere, you don't have time to plot, you don't have time to really dig into what's going on, but you want to get a feel for like the quality of the data. Again, if we kind of now inspect it, knowing what we know, this is TP9 and this is TP10. So visually, the idea was that TP9 is going to be a little more what we want. TP10 is going to be a little noisier. So let's go down and look at these voltages, right? Now we're seeing stuff around plus or minus 30, 40 microvolts at the electrode. And over here, we are very much outside that range. We're 200, 130. Okay, now we've flattened out. Now we're back out. So these oscillations are too much. It's not the sign of a good fit. Yes, there's noise on both, but when TP9 behaves itself, it kind of returns to that range. Right now we're in the 20s and 30s, and over here, again, we're in the 90s and 100s. So again, just something we've observed with using the Muse device. Let's say plus or minus 30 or 40 are good stuff. Maybe even a little less, but let's just be more generous and say 30 to 40 microvolt oscillations. And if you get it beyond that, it's probably a sign of a loose electrode fit. So for the most part, you're just using some tool, recorder, or whatever to connect to the stream and store it in this format that's basically going to be timestamp, voltage on the electrode, label for the electrode, and in the case of the Muse, there is an auxiliary port that also gives a reading, but unless you have an electrode plugged in, you won't get anything useful out of it. Okay, so I'm going to stop the screen sharing for a moment, and let's put on the camera. Does anybody have any questions about, let's say, recording the EEG data, taking a look at it? Has anyone tried it and had any difficulties like that? Is the screen not showing?
It's been working.
Okay, you were able to see the recording. Okay.
Yeah.
Okay, great. Excellent. Okay, so that, well, let's see. Mr. Jaden, not to put you on the spot or anything, but do you have the Neurosity one? Do you have an app that lets you record the data? Maybe we can replicate it as well. If not, we can take a look at some of the other stuff and see if we can record either on Mind Monitor. I think John's going to do that a little bit later, or we can just sort of look for another device.
I'm sorry, to do what?
Could you do a recording real quick on the Neurosity? Do you have an app that lets you store the data?
Yeah, I don't have much for showing the data yet, but I can at least store it.
Mm-hmm. Yeah, and then just open it up in a editor to take a look at. I figured it'd be useful to show people how different the Neurosity voltages tend to be than the Muse.
Yeah, let me get my device out real quick.
Cool.
I hope it's still charged. My one complaint about these devices is that they don't hold a charge when you're not using them.
I have that issue with all our EEG gear.
That sounds like either a grounding issue or a phantom draw from something, which
I think it's like an always on type deal.
Oh.
Yeah. I forget what the reasoning for it is, but I'm sure I probably don't agree with the decision, but
yeah,
that's neither here nor there. It's a tiny little complaint for an overall fantastic product.
Yeah. I mean, I always like when things like that can have an external battery, and you can just completely disable the internal one, because sometimes that can also get rid of certain noise artifacts if that battery's integrated really tightly into the circuit and can create EMF.
Yeah. Come on. It's on. It's just not. My computer is not picking it up. Yeah, I think I might need a charge for a little bit.
That's
Did you hear me, Alex?
fine. Yeah. Yeah, I do know it's going to be a while before John shows up. And I don't see I'm
Okay.
bad with names.
Yeah, this is
Sure.
weird. Even when I plugged it in, my computer's not recognizing it.
Cool. Well, how about you take a little time? I'll do a little bit of the data analysis, or like sort of the data, taking a look at data. I mean, it's a little, different scheduling wise than we were, but who cares? Let's take a look at actually
Oh,
recording
hey, I
some
think I
data.
might actually be
Oh,
good.
all
Let me
right.
just go ahead and go to the mirror real quick and put it on to make sure it's making contact, and I'll be right back.
Mm-hmm.
Let me go get my earbuds too, because I realize I'm not going to be able to wear these headphones with this on.
Right.
The eternal issue. Can you fit your headset and headphones on at once?
That's why I have to wear earbuds. It doesn't work with the Muse. So yeah, or I mean, you know what I mean. It's cumbersome having a headset. So
Yeah.
so this kind of makes life easier.
I also wonder if headphones would cause any EMF issues for nearby electrodes. Like, I mean, you can kind of create low EMF headphones if you like, depending on if they're open back or closed back, and if you're doing like electrostatic or dynamic drivers or magnetic ones. But I feel that could increase the noise floor quite a bit for sensors nearby. I'd actually love to find out, because I bet um Neurable had to deal with that with their headphones they're releasing. So I might ask them. Um yeah. You're muted, Alex.
It's even tricky in the sense of if the headphones had enough bass, I think you could pick that up on the electrode if there was vibration. Yeah. So earbuds definitely make life easier if you're trying to do audio. That's for sure.
Yeah. Though high quality earbuds are so expensive.
Yeah, I've been impressed at how high those prices have climbed.
Oh yeah. I mean, I've seen some like I once or twice tried electrostatic IEMs, and they sound amazing, but they need a massive preamp the size of like a phone, just to get the voltage high enough to actually power them.
Right.
And I am planning to actually make some, because the cost of making electrostatic drivers is really low now that flexible PCB printing is cheap as all heck. And yeah, I'm going to have a lot of fun making some audio gear at some point, and I'm not going to have a headband. I'm going to make it so they can like clip on to VR headsets or clip on to EEG headsets.
Right.
But yeah, if there's an EMF issue, I'll have to really think a lot about it.
Right.
Yeah.
All right, let me just
Will
test
look
my
like
signal
data
quality.
back.
All right.
All right, we're looking good on signal quality, so let's do it.
Cool.
Let me share my screen. Do you want me to live code it?
Oh, that'd be wonderful. If you're gonna write a few lines of code to store the LSL data, yeah.
Okay, let me.
If that's too tedious, I can always send you our LSL recorder if you want.
So it won't be over LSL, it'll be over BrainFlow.
BrainFlow. Oh, even better.
Which uses for Notion, it uses Open Sound Control.
OSC. Okay.
Yeah. All right. Cool. Can you see that?
Yes.
Is it readable or is it too small?
No. Well, I'll let other people, but for me, it looks fine.
All right. So let's write some. So the first thing we want to do is we're going to record the data. BrainFlow requires, they have a class for their input parameters. And so you want to just define that variable first. Let me open up a new cell. Hopefully I don't make too many mistakes doing this. I've actually never done live coding before. So
I'm psyched. I mean, this is a lot of folks, might be watching sometime down the road wanting to write their own interface to BrainFlow for some device. Just kind of cool that there might be a video for them to look at as a reference.
yeah, that's a good way to think about it. Riddled with potential mistakes. So the parameters that BrainFlow needs to start is dependent on the device, and you can find that on their read the docs. Like for OpenBCI, for example, you need to give it a USB port that the dongle is in. Although I think now that they have a way to automatically discover it as well, so you don't even need to give that anymore. But for the Notion, you don't need to give anything except for its board ID, which is something you need to give for every board. So we'll define that as well. And so they're nice and named already in the class. The Notion OSC board, I believe, is I'm not sure if it's for their device emulator or Neurosity also has a like OSC streamer that they use for testing on the back end. So it could be for that as well. I'm not quite sure, but depending on which device you have, you'll either want to do the Notion 1 or 2. And I assume that there's going to be a new one coming out for Crown as well.
Mm-hmm.
And so now we create the board device.
Can you possibly zoom in a bit so that the...
Oh, that's great.
Yeah,
okay.
that makes
I don't know
much easier.
I don't know if I can zoom in on the right-hand side, unfortunately.
Oh no. Wait, are you in
I'm in PyCharm.
Oh, I haven't used that, so not sure.
It looks fine. Looks fine. I think the one on the left is the perfect.
Yeah, the right hand side will at least show the like output of graphs and stuff. So
Couldn't
that'll be
you
useful.
use? Are you on Linux or Windows? Could you do a just window scaling, or
I'm
display
on
scale?
I think
I'm
this.
on Windows right now.
This seems
This
fine.
is probably fine.
Yeah.
So now we just pass both the board ID and the param object to the board shim, which is their main class for all of the boards. And we prepare the session. So notebook kernel doesn't match project interpreter. Well, let's hope that doesn't come back to bite me in a few minutes. All right, so now let's say I want to record 30 seconds of data. We need to start the stream. And that'll start it in a background thread running indefinitely for as long as you want. And so I could just run that cell right now and have it record data, but to make sure that it records, a specific amount of time, let's say 30 seconds, I'm going to just set a time.sleep. I need to import time first. And so that'll wait 30 seconds. Then we're going to pull the data from the board. And so this command right here, get board data, will actually remove all the data from BrainFlow's buffer. There's another command that you can use, which will be get current data from board, I believe.
Okay.
And you can give that a certain amount of sample numbers. It'll pull the last X amount of samples, but it'll still leave them in the buffer as well. So you could pull all the data if you want later.
Okay.
So now we can stop the session as well. And after we stop the stream, we want to release the session. And they have a built-in function in BrainFlow for writing the data to a CSV file. So now I'll just sit still for 30 seconds. Oh, that's strange. Oh, it needs to be. Cool.
All right.
Accept. Where did it put the data?
Jaden, are you screen sharing right now?
Yes. Can you not see?
I don't see. There's something I have to press to make that visible.
Maybe if you click my square.
Yeah, it has to be in focus.
Yeah,
Otherwise,
I have it in focus, but is there something else I have to press?
Might take maybe he has to stop and reshare it if you joined.
Oh, okay.
It might be like some kind of glitch.
Don't worry. Don't mind me. Don't want to interrupt.
I'll do it real quick.
Yeah, good to see that.
Perfect.
Okay. Oh, there we go. The file showed up. Just guess PyCharm took a minute to update. Cool. So now that the file is saved, we can load the data. So it's that's CSV. And let's turn it into a data frame to plot it. Already import it. Then if we want to get a look at it, I believe Pandas has a plot function built in. So first we want to get so whenever we store it as a data frame, I guess we could check out the shape of it real quick.
Mm-hmm.
So it's 12 columns, but there's only 8 EEG channels that we want. And so the rest of it is either like the timestamp or other signals that they have going on. So luckily, we don't need to intuitively know which of the channels are the EEG channels because BrainFlow also has that built in. So we're going to do EEG channels is equal to board shim dot, I think it's get EEG channels and the board ID. And then we could do plot df. Or no, that's not right. It would be, I need to import matplotlib. ELT.figure. Believe ELT.show. Oh, well, let me save it and then I can open it up. All right, we'll give that a minute to update. There we go. Oh, okay. Well, that's still terrible quality. Well then, let me.
Give it more DPI.
So the for some reason I guess I could try it in there. It doesn't let me zoom into stuff on the right-hand side. I don't know what the command for increasing it in the.
I think it's fig.ax if you want to expand the axis, or like there's a way you can define like 16 by 9, which I think is the same thing.
Here we go.
Yeah, perfect.
I could just copy it and put it into another file.
Even better.
So You can see that like the values are really kind of off, and that's because you haven't like done any of the filtering out of the DC offset yet, or really anything. This is just pure raw data, and so this is virtually useless in this form. Luckily, BrainFlow has other functions for like running bandpass filters and stuff like that, which I'm not sure you guys want to see me fumble through right now, because that will actually be riddled with errors and typos and probably take painfully long.
Yeah.
What's the advantage of that? Are they fast? The BrainFlow filtering things, like will they facilitate like real time stuff, for example?
I think in theory, yeah, they're pretty fast. I haven't really tried using them in real time, but I think because BrainFlow could work in real time, like you're just pulling data as you need it, it would save you the step of loading things into an MNE object and having to run things in that regard. I think it's meant to be quick for that purpose.
Okay.
Yeah.
Yeah, and maybe if you would open the Excel file real quick, I'm sorry, the CSV file real quick, in whatever is a good, perfect. Okay, so if we compare it to the Muse, these voltages are very, very different. And that's because the Neurosity uses active electrodes instead of passive electrodes. So electricity is injected at the electrode and sent to the, it's already amplified before it gets to the circuit board to reduce noise. And what that means is that you're going to have very different values on the very different channels. So you'll notice the first channel is around negative 3,000 microvolts. The second channel is at positive, is that 18,000 microvolts?
Yes.
Yeah, about that.
Yeah, the first one was negative 33,000.
Oh, wow. Okay, negative 33,000, positive 18,000, then negative 3,000, negative 30,000, negative 35,000, negative 1,500, and so on and so on. So the voltages are all over the place, but it really doesn't matter what the voltage is. And I know that sounds kind of like a counterintuitive thing, but when you put it in the Fourier, you're going to get back the frequency power. And of course, there's the filtering and all those other things that Jaden mentioned. But I wanted to show you that it doesn't matter if the voltages are goofy. The Fourier will look at the oscillations in the signal, it will look at the fluctuations, and it will reconstruct what signals were present that caused those fluctuations. So it's okay if each electrode is in its own zip code in terms of what it reports as voltage. It's okay if the, montage doesn't agree. Yeah, sorry.
Does anyone know like what the pros and cons are to that design feature? I mean, is it just straight up like active electrodes are better for this type of, for this type of device with this type of, tech components? Is it just kind of a markup, or are there like some pros and some cons, not just cost, to having active rather than passive electrodes?
I don't know of many cons, but the pros at least are just data quality, because it's less time for any noise to get into the signal, because it's amplified right there where the electrode is, versus taking, because like with the open BCI, for example, you have all those little wire connections that it takes to get there. It's not shielded, so there's EMF hitting it. Right. And so active electrodes, it tries to eliminate that at the source.
Yeah, I mean, that's my understanding. I think that's like this, this received wisdom in general with active electrodes, but just given that we sometimes have a kind of an engineering crowd, I don't know it at a detailed, circuit engineering level if there are also some negatives to having that part of this, circuitry in there.
I think it's just power.
My sense is that it adds a lot of cost and complexity to any hardware that includes it. So for example, the last device that I got to experiment with that had active electrodes was the wearable sensing DSI 7. And that's wonderful. It's got these double silver wrapped electrodes. So it's like an electrode within an electrode, so that the outer one acts as like sort of a shield and all this other stuff. And they had the active electrode scheme. But that's that's an expensive device because it's so precise and high quality. The Muse is sort of a $200 form factor, and I think a lot of this has to do with the amplifier design and the circuit design. So from what I understand, the Muse uses a driven right leg circuit. Is that what they call it? The DRL? I think it is.
I don't know.
I think it's called I know for sure it's driven leg, but I think it's actually driven right leg for whatever reason. So the Muse uses that, which is sort of like, I think, an older, more well-established, whatever. They were, I think, really trying to hit that super affordable price point, and they really succeeded. I mean, that's why we've been using Muses for years. But the fascinating thing about the Neurosity is that it kind of brings in these features that you would need to pay multi-thousands of dollars for, and brings it to like this $900 price point. I suppose if it adds another layer of complexity, you have to trust that the amplifier works properly. You have to trust that you have to deal with the extra complexity of these sort of voltage ranges that are all over the place. So I suppose it induces sort of an extra element that you have to trust. But from what we've seen, it just seems to generate better signal if you can deal with it.
Yeah.
Is it kind of adjusting in? Is a circuit adjusting the injected amplitudes to
based on the impedance of the connection. Yeah, to keep it within the spec of the amplifier. That's the explanation that so the amplifier has like a voltage spec where it can operate, and the closer it gets to the extremes, the more noise the amplifier itself is gonna. It's the same thing with the receivers. I think they call it like total harmonic distortion ratio, and like you want a receiver that's like 0.01 is great, 0.08 is like crappy or whatever. And so I think you could probably rate these amplifiers in terms of distortion that they introduce in the amplification. And, I certainly don't know the Neurosity design, but in the wearable sensing, you wanted to be aware of electrodes that were completely at the limits of the amplifier. We're just not going to get, good signal, and it usually meant that you had an impedance problem, that you wanted it to have a decent impedance, so the amplifier didn't have to go to like a wacky config to try to deal with the impedance mismatch.
Yeah, right. I guess we just kind of put faith in the circuit design and the developers that there aren't kind of systematic artifacts introduced when you're kind of pushing the current injections over to the noisier and then trying to kind of pull signal out of nothing.
Right.
If there are other channels like not even on your head.
Right. Or if you've got hair directly blocking the electrode, I think that's kind of like a common issue.
Cool. Well, sorry to interrupt.
Oh, no. Thank you so much for asking that.
Be interested in the various new differentiating aspects of the Neurosity devices.
Yes, I'm really excited that they implemented this stuff. I think we are getting our Neurosity gear somewhere in the next week or two. So hopefully right after this spicy challenge is complete, I'll be able to start doing demos with the Neurosity gear as well as the Muse. And then I need to order a Unicorn Black, I think.
Cool. So I think I'm done on my end.
Beautiful. Thank you so much, Aiden.
Yeah, of course.
And maybe we can, after the call, it doesn't really need to be whatever, but if we can maybe just record a short clip of something we'd be comfortable, if you send it to me, I'll put it on some kind of thing so that we can also reference these files as part of the hack night. Or you don't have to if you're not comfortable. I'm sure I can find some source for these.
I mean, I could send you the file I just recorded.
Perfect.
Yeah.
Just so people can take a look at it. Yeah.
Yeah, of course.
Beautiful. Okay. Mr. John, would you like to show us how to record a file with Mind Monitor?
Right. Yeah, I can do that. Give me a second to just plug in and turn on.
Yes.
Let's do some
If
more
anyone
small
has,
talk.
yeah, if anyone has any questions on either the Muse portion, by the way, if you might, I'm a Muse LSL scrub, and I embarrassed myself when you weren't here to save me from a disaster. So when I try doing a recording with Muse LSL, it plays sad trombone noises instead.
Okay, so is that something we want to revisit?
Yeah. You might actually be able to help me fix it.
Did you have errors, or would you just forget what the syntax was?
No. I made it past that challenge. Luckily.
Yeah. Okay. Well, let's see if we can get to that.
Cool. All right.
Yeah, I'm still turning on, so we can still kind of chat and stuff. But this will be relatively brief because it'll be kind of a demo. I kind of demoed the app last time, and it will really just be kind of save it and then see what happens.
Yeah, just so we can kind of see what the the Muse on a smartphone looks like. If you can just open that Excel, or if you send it to me, I can open it if that's easier. Whatever.
Well, what I'll do is I'll send it to Google Drive, and then I'll pull it up in a Colab notebook on my laptop.
Even better.
Once it's been sent.
Yeah. And out of curiosity, Daniel, Jenny, and Valerie, and Nivi, do you currently have any EEG devices that you're looking to potentially connect or collect data or something like that? Maybe you can just drop it in chat because it'd be great to focus on anything you're actually looking to do. All right. Valerie is negative on that. All right.
I got a Muse recently, so I've tried setting it up, and yeah, I can definitely do some data collection next week.
Great.
I had a question. So the last week, I was trying to go through the video without the audio. So I was just trying to put things together based on what I could see. But there was this one Curia plotter, which I wasn't able to remember what the source was for.
That's, you have me to thank for that confusion. The source is our startup, and I didn't have an easy way to sort of show those plots. So yeah, that's our plotter that we use to make graphical videos. Yeah, I'm super. that's great. Yeah, I'll try to make a clear caution of this is our stuff, so people aren't wondering where the heck that
because
is.
I was trying to look it up, and I wasn't able to remember exactly.
Okay. Yes. Yes. You're gonna have a hard time finding it.
Okay. Wait. Thanks.
Sure. But you can use the Muse LSL view functionality. It'll at least get you the raw, but it won't get you the power, the band power.
Yeah, I was trying to get the FFT and the band.
Yes, we will definitely cover how to view that hopefully next week.
So that would be real time?
I haven't looked into if someone's got a real-time plotter. The OpenBCI GUI does let you do it. I think the Neurosity, you can do it. Obviously, if you write some Python code, you can do it as well. You can stream through Python. So I'll definitely. What operating system are you using?
Windows.
Excellent. So I'll have a plotting. I'll have an answer for you on whether there's a package that you can use to plot the power spectrum and the potentially the band power on Windows in real time.
Okay, great. Thanks so much.
Absolutely.
I could try to, no guarantees, but by next time I could try to write something in Python.
Perfect.
Oh wait, but using LSL, huh? I could try. No guarantees.
Well, I might be able to do like a matplotlib script that hooks into LSL because we have written a few Python LSL aware things. So yeah, but I think it would be great to have a plotter that people can use because that's always been a bummer for me to not have that.
Yeah, maybe it'd be good to have for EG notebooks as well.
Right.
I missed a bit of this. What was the question?
Talking about making like a real-time plotter for like the free power spectrum or the frequency bands.
Real time, yeah. Yeah, that would be handy.
Yeah, like I think right now if there's an easy way to, because can't OpenBCI GUI, doesn't that use BrainFlow? Which BrainFlow can use a lot of these different headsets. So maybe there's, because the OpenBCI GUI is, I think, on GitHub. Theoretically, that could probably be made to work with any BrainFlow
Get some
headset.
Java. We could definitely
But
take a
that-
look at it.
Yeah, I don't want to rewrite their whole
GUI.
GUI. It seems like a lot of work.
Yeah.
I think we could because Matplotlib has like an animation package, right? For doing
I think
real time
so.
stuff.
I think so.
So yeah, we could use BrainFlow to do that easily.
Yeah. Or at the very least, we could update it some janky, right? Yeah, let's take a look at you know, having something. We can chat on Slack to see if we can have something ready for next Thursday's HackNet. I think it'd be great.
Yeah, I mean, that also would be a good hackathon at some point, is like
Yes.
help us create a visual, like pretty much, yeah, crowdsource the GUI real time.
Let's just make tons of hack nights where we crowdsource new features for EG notebooks.
Yes.
Yeah, pretty much.
I like it. I like it. No, it would be cool to have that in
Can
EG notebooks.
can
Yeah.
you look at real time data in EG notebooks right now, or?
Not right now, but it uses BrainFlow, and you can do that using BrainFlow. So,
Right.
So yeah,
So-
so if it has a real-time connection to the BrainFlow, yeah, that would be really cool, because then you don't have to upload anything. It's already just there when you're done.
So Nevi, thank you so much for mentioning that, because as you can see, you inspired us to correct that. So thank you so much.
Yeah, I would
that-
like to take part in the feature development stuff as well. That would be fun.
Ooh,
Okay, great.
yes,
Great.
of course. Of course.
Okay, and Daniel, is everything? Did you have a device?
Yeah, I was just so I got a Muse, and the challenge is that I have to get the Bled dongle for Mac.
Oh yes, the
And
Bled 112.
I couldn't find anything on Amazon that like ships with Prime. So I asked on the Slack channel, and someone recommended this Petal Metrics, and I got like an LSL stream. So I got the stream, but I cannot view it. So I'm looking into how to. It's just like a raw stream, like 5 numbers.
But you can save it as well. Did you try to save it? Because I got the message from Dan. They've added a saving functionality now to the Petal app, I think. Does that ring a bell?
No, they don't have it yet. I mean, I haven't seen it. But,
Oh, okay.
I'm just writing a little script now that just saves it. But it's unclear like which one is which.
Yeah. So
use
currently like that tool they have is in the kind of same space as Blue Muse, filling that kind of gap, and I think might, could potentially, do a better job at some point. They certainly seem to be putting a fair amount of active development into it, but it's still kind of new. I tried it out. I got a connection, but I got a message from Dan. I thought they said that they had some saving functionality, which sounded kind of handy, but I haven't got to checking that yet.
Are you in the United States?
Yeah.
If you go to, it's not going to be Prime, but there's Silicon Labs is the company that manufactures the Bled 112.
Okay.
And if you Google Silicon Labs Bled 112, it's the Blue Giga Legacy modules, whatever. They have a distributor that can ship them out for $11.50, or I'm sorry, like $12. and they can do batches of 1 to 24. So, you know, if you just get like, I don't know, 2, I did that in case I lose it, then I've had, I did order from them and I got it in 3-4 days. So I'm not saying it's like, it's not like Prime, but it's not horrible either.
Yeah, it's not like 3 weeks.
Yeah, it's not being sent from mainland China.
Sounds good. Yeah, thank you.
Sure.
So I have a stream going here, but I've noticed, I don't know if anyone else has noticed, that there's some serious artifact going on in the temporal channels.
Yeah.
And the reason why you can tell that is because it's like very oscillatory, and brain data doesn't look like that as a rule. It might be the headphones that I'm also putting in. But yeah, it's just kind of an observation, not something that we need to dwell on right now. Let's continue. So we talked about what you can do in here last time, so I'm not going to repeat that. But as you will have saw if you were looking just now, like I connected and we have the stream. I mean, just very briefly, as we saw last time, we can look at some of these other functionalities. I wonder if that artifact will come up on the power spectrum. I wonder if we'll get a kind of strong, narrow peak.
Yeah,
somewhere.
there it is. Yep.
No, I think it was slower than that. That's the mains line, that.
Oh, yeah. You're in Canada's 50 hertz?
Yeah.
Okay.
Yeah.
Okay.
I'm not seeing any really crazy ones there. Anyway, the main thing that I want to do is just demo this. This is super quick, right? But what I'll do after this is I'll show you what I'll open the file. But so press record. Maybe we'll sit here for 20 seconds or so.
I can trouble you for a blink as well. All right.
Some jaw clenches there.
Excellent.
Okay, I think that'll do.
Perfect.
Press stop. And then, so first thing it does is it zips the data. And because that was a short recording, that was pretty quick. Obviously, if you do several hours, then it takes a while. And I haven't kind of fully road tested when it struggles, let's say, with large files. I'm curious how long you can do recordings with my monitor, and it seems it's very phone dependent. Basically, it's very hardware dependent what you're running it on. But generally, it does a good job with most things that I've tried. So now I selected send to Google Drive. So now it's pulling up my folder, my Google Drive folders, and this is how I organize my life, guys. So this would be sciencing. That's what we're doing right now.
Oh,
actually,
wow.
data. So I actually have a folder where I put my monitor files because I've done this plenty of times before. Right. So that is Muse Monitor. Because it used to be called Muse Monitor, and then I guess Muse sued them or something, and then they had to change. So Muse Monitor recordings, and as you can see, I've made a bunch of files before. So I'm just going to dump this one in here. What it's going to, first thing it's going to do is going to give me a zip file, right? So we're going to have to unzip it when we take a look at it. But if we leave it at that, so I mean, other things I guess quickly is as you will have seen, and I can do it quickly if I just press record and then press stop again. These options, so it's like a share option, right? That probably people are familiar with on their phones. So you know, I could send it by email, or I could send it, you know, there are lots of options for how you can move these files around depending on the device that you have. But for me, saving to Google Drive is definitely like the most useful thing, because I do a lot of my data and kind of life organization in there. So I'm gonna tune out on the app now. I'm gonna kill my Jitsi on there, and I'm going to start screen sharing on my laptop. Let's take a look at the file.
All right.
So I didn't open the files in advance, so I'm just going to kind of assume that everything will go swimmingly. That's how you do it, right, Alex?
Yes, that's how I did it, and it went
that's
great.
What I'm going to assume, that there's no problem with you guys seeing some of my personal folder stuff, but this is where we were just now. Data, news monitor. So the next thing that some people are probably familiar with, but perhaps not everyone, is using Google Colab to look at stuff in Google Drive. So I have that notebook there and some other ones. Just going to quickly have a look, see if I have any other useful notebooks in here right now. That's for the other stuff. Yeah, this will do the trick. All right. Do I need to give any sensitive information when I do this? No, I just type in a password, don't I? Okay, should be fine.
Yeah. Can you zoom in?
Yeah, sure. Right.
Excellent.
Yep.
That's
so like one or two things about Colab notebooks for people who aren't so familiar. They operate a lot like, well, they are indeed like basically Jupyter notebooks, but a few differences is you need to install any non-standard. You don't have like persistent environments with installed stuff. Every time you log in, basically, or you initiate a Colab instance, you get a fresh OS and a fresh kind of Python instance, and anything you want to use that's not kind of part of the broad but kind of standard Python scientific computing stack, you have to do an install command at the top. So we'll do that. Fairly quick. I'm going to do some Python imports. So the M&E is a Python library for EEG and MEG data analysis, and a workhorse for a lot of the things that I do, and definitely you should check it out if you're planning on doing Python-based EEG data analysis. Now, is accessing your own Google, which not everyone is familiar with, but the process we'll get into in a second. Okay, I have a function for loading data, which we can go to. Goes, but a line that my Google Drive in this Colab notebook. I just need to authorize it. So it gives you a link to just click on. Give me just something to copy paste. Just copy that and put it in this code here. And now this Colab notebook has access to my Google Drive. So one thing that is worth understanding is, even though I launched this from this folder, right, in my Google Drive, that's not where it starts. Where it starts is default location. That thing about content of your Google Drive is kind of just a server in the ether, right?
Mm-hmm.
But now I've mounted my Google Drive as a file path on there to the contents of my Google Drive as a mounted folder. And that's how we're going to, so that we take a look at it. So as you can kind of see, as you can see, I just browse this a second. Okay. So this was the location that I mounted my drive. So this is kind of the top level of my Google Drive. Oh. Did I spell something wrong there? Yeah.
Oh, there's a muse.
Yeah, I missed the folder in the middle. Right. So now this is actually a folder that and this is the notebook that I opened up just as a kind of observation. Doesn't really matter right now. What matters more is the data files. Recorded just now, if we can kind of pull it out. Slow internet. Uh, 6th of April. There you go. So this was the one that we just created, and in the interest of time, it was copy paste this file name. So file this. I'm actually going to navigate to this folder to put this in. Yeah, I think I want to be in MM. Yeah. So within MM, okay, so I don't need this long. I can just use file equals that. This one down. Let's just check that I've got that right. Oh, it's the panel. Oh, what did I get wrong? Recordings, wasn't it? That was it.
Yes.
Okay, there we go. So we know about that file. Now, this notebook has some stuff that I don't necessarily want to use any of, I don't think, completely scrum from the start with. So so we'll start with our file there. It's a zip file, so we can't load it in directly as a zip file. So the simple thing is just do unzip. I don't think I used the Python. Oh, I did. I used SHU. So we get the Python library. So that's just a kind of Python wrapper on a unzip command, which you could do like that. Just drop down to Linux, and so our file unzipped. I think in the same location, or maybe it'll have gone into the one that we're in right now. I think it should be CSV. If that exists. Is it in the folder I'm currently in? Yeah, okay, so simple enough. I unzipped, and then got the contents in the folder. So here's the file we want to load in. Now, simple to do that. Pandas, very good for I/O.
Pandas really makes. Yeah, just to add to what John's saying for a moment, the Pandas makes life easy in Python. If you want to read CSVs, if you want to do data frames, but really it's incredible how easy it is to read CSVs. You know, when we were experimenting, we used XDF for a long time, but CSVs are just phenomenal in the sense of what you can do with them in Pandas. Might seem like a boring file format, but it works great.
Yeah. Like reading, writing, manipulating. So I live in Pandas, but I think those Pandas, the alternative, you know, what would you do? You do like open this, right?
Alex and Jaden, can you turn off your video a bit? The bandwidth is a bit high. I think it's John keeps cutting out audio wise on my end. Yeah.
Sure, I cut the camera.
That
all right,
help.
Clicking back to John. All right.
Yeah, maybe read it as like plain text.
Hey, John, we're back. Mm-hmm.
Yep. That was just a side point. So data in a Pandas data frame. So, you know, it's basically the same kind of thing that that Jaden was showing us, in that it's a CSV. Actually, so what we've got here: delta, theta power, alpha power, beta power. Right, all those kind of band specific powers. We've got the raw, which we'll look at in a second. I've got and
okay, great. Can I take a moment here and point something out?
Yeah, these are some other of those. Go for it.
Yeah, sorry to interrupt. If you could put us on the raw voltage for a moment, I just wanted to show that it does look quite different, even though it's the same device from the things that we looked at previously. So
right.
This
well, I'm gonna do the raw in a second.
Records in. Oh, I'm sorry about that.
I was just gonna ask Alex. So these ones here, headband on and HSI, Do you know what HSI is?
Mm-hmm.
Is that a signal quality thing?
They had a doc that listed all their little flags. Headband on off is definitely an event. This is all stuff off the DSP. I can check their docs right now to see what the HSI value is. Yeah.
Like in a nutshell, like these are numbers that are coming from the Muse device that are kind of like computed on the and alongside the other.
Okay, that's
the other like EEG data, right?
Yeah, so HSI is electrode quality. We had the same metric from the SDK when we were using it. So it's a scale of 1 to 4. 1 is equivalent to the green in the app. 2 is equivalent to the yellow. 3 is equivalent to the red, and 4 is equivalent to the black, which means like no connection.
Right. Right.
Headband on is the data at all usable, and it's a Boolean 1 or 0. If the headband is off your head, it should show a 0, but if you're wearing it, it should show a 1.
Yeah. Good. I've never actually used those numbers, but it's kind of neat that that my monitor does spit.
Yes, one of the things that's cool is if you have a script that might not use. Yeah, if you're trying to select channels automatically, you can kind of go by the lowest HSI value.
Just pull the raw channels from the data frame, be like so. So yeah, these are the raw numbers, and we could look at the range. So I would do that with a histogram. Maybe the kind of overlapping actually alpha. ADs would be a bit look at that.
So some apps like Muse LSL and Blue Muse will center this around 0. So this is the third different set of voltages that you've seen on today's calls, right? And in the first block, it was all around 0, and we were looking for things that were like plus or minus 40. And when we saw, plus 200, it's like, ooh, that's a lot, right? We know that electrode is out of spec or whatever. There's another way to count, which is to go off of the absolute voltage that the electrode is recording. So in that case, you're not subtracting the voltage from itself so that it zeroes out. You're leaving it in the raw form. If you're ever just recording raw voltage, this is what you're going to get on a Muse. Typical values are somewhere in the 850 microvolt to let's say 800 to 950. I don't know, something like that. But if you're over 1,000, that's kind of weird. And if you're under 700, that's kind of weird too. So hopefully this gives you some idea of what you're looking for when you look at your raw data. If you use Mind Monitor, you're going to want it to be around, 880 is sort of a good voltage, 850. Those are kind of good numbers. And if you're using Muse LSL, you're going to want to see them around 0 with oscillations of 20 to 40.
Right. And, kind of interesting point there is that the raw channel, the auxiliary channel, which doesn't have any brain data coming in, this is like a noise channel, that's in a similar range to all of the EEG channels. So that's that is the background level. We can see those oscillations, though, that kind of noisy signal that I had in my temporal channel. I mean, that's super clear here. But let's do a little bit more playing around with this data. So we had, what do we do? You asked me to blink. I did. So we do.
Yes, you did a blink and some jaw clenches.
Whole range.
Mm-hmm.
Yeah. I mean, this is a mess, right? So right now, it's not good. It's really not good. But the reason, I mean, I'm inclined to say that I could have spent a bit more time adjusting the channel. I could have on, and I think maybe the headphones that I had in my ears were possibly given a bit of contamination, but I'm still a bit unhappy with.
I think this is great.
Noise.
Well, in my experience, if you're first starting out on a Muse, you're going to tend to get noisy recordings. So I think this is really representative of what people that are experimenting with a Muse are going to experience.
Absolutely. Oh yeah, it's definitely representative. Yeah. So we said before that I put the thing on. I had it on for 15 seconds or so, and I spent a bit of time blinking, and then I spent a bit of time clenching my jaw. And this is what you're seeing. This kind of middle, that was when I was a bit on the right hand side. That's when I was clenching my jaw. And that's something when you're doing recordings that are not super long, then it can be kind of helpful just for demarcating things that you're doing to do something like that, just so you can kind of see it in the time series. You know where it gives you a kind of extra kind of anchor point to know when events are happening without formally tagging events using timestamps, which is a slightly more sophisticated thing that we'll be probably talking about next week. But I can see, so no, for example, like if I wanted to record resting, eyes closed, or spicy food level 1, I could start that after my first set of jaw clenches, right? And that would give me, without even having to kind of reference the timestamps or my watches or anything, I'd know roughly where to cut it up. So that's something that's kind of worth thinking about for certain types of things. It can be like a little bit helpful for interactive, very quick data manipulation and data kind of, how do you say, wrangling.
Yes,
Yeah,
that's a wonderful suggestion, John. I also used to use 3 blinks in a series as sort of my event boundaries. The exact same thing, the exact same reason. It's just that since I knew there was exactly 3 of them, I could find it pretty easily.
So something that I can do, and I will straight up the settings. Is actually getting full light. Can do that quite easily. Back up here to do df.set. So you see this is one of the, but that makes sense. Give basically the labels for the column. Sorry. So set index timestamp place equals true. Then now it's there as the column. I can, one. It's already got a name, so I don't need to do anything. Cool. So then helpful for these ones that we were doing, we'll get now. Okay, but now I have to do something different with my indexing for lock. I'll do iLock. That would be fine. Do .iLock. That just goes in kind of integer unit sample units rather than trying to actually use the magnitude of the indices there. So that will give me the same thing, same thing. Yeah, I mean, my timestamps kind of getting in the way of each other now because I'm going to do rot equals 45 or that. Yeah, that helps. So timestamps are getting in the way of it, but we do actually on the x-axis in kind of 2216 43 to 2216 44, right? So let's maybe do a quick power spectrum, and then I think I'll call it a day, but I'll point to one or two other things before I wrap up. So power spectrum super easy from sci-fi.signal import Welch. There are other ways. That's my preferred way. Give it the data, and then what that's going to give me is frequencies and amplitudes, and the thing that I need to give it. Just curious. A string in there, so okay, I'll just select the raw channel in there. Right. Now, the thing that I always forget when I'm doing this is which way around these two come. And that's easy to check because frequency numbers should be in array, same number of columns as. Okay, so I know now that I need to transpose because this should be along, kind of maybe be a bit clearer in a second. This should be, depending on the sample length, like 1 or 0.1 to 40 hertz, 100 hertz. So that's my frequencies. Now, the other thing that I need to get right when I'm asking for a Welch power spectrum is the sampling rate, which I can calculate from the time index. Take the 256 hertz. So actually, probably you can know it. I could do it like this. These are timestamps, so what happens when you do a diff on a time? Just a number. They were really straightforward. Well, shouldn't be too hard. They're strings, aren't they? They're not timestamps. Wow, what are you doing this? Okay, cut off that. I just need, what I need is just the difference between the first two. So I think I'm here. Off the end of it. Split off after that. Take that. Trying to get it down, trying to get seconds difference. And my second timestamp, I'm trying to get it down to too close. Maybe we'll just assume that the sampling rate is 250 Hz. So I think the frequency scaling we want to put is going to be 1 over the sampling rate, which is another thing that I kind of always forget when I'm doing these things, and just kind of do a combination of trial and error and checking back over how. But the way to know is the range of frequencies that we get out of it. Which isn't right. So there's 256. Yeah, that's right. Yeah, I think so.
Yeah, it definitely looks
then
like
again,
let's
put it in a. Yeah. So amps and then index equals frequencies. Into the columns afterwards. BF power spectrum. What's this? Yeah. Oh, you give me a bunch of nans? Oh, what does he wrong? Are these strings? They have symbols. They're floats. Why did I get a bunch of? But maybe there's a nan in there somewhere. Or a nan in there somewhere.
How many times we've had to run the isnan command?
Yeah. Is null in a pandas. There's 52 nans in there. So I'll do a drop. Maybe that was when I was doing my jaw clenching. So do drop an A. So yeah. Okay. Going too nuts. I mean, this is very questionable because there could be kind of large cities next to each other. In the interest of just getting some results in. So get rid of our nans. Yeah. now do what we said before, but let's put this in a data frame. Good. More chance. All right, so we have spectrum. Frame here. Let's see what. Okay, so first thing I guess to say is I was doing a log power spectrum plot there, which is not the most intuitive. It's got a lot of time series and other types of data that is actually a good way of plotting things. And just to kind of concretely is well, so this giant thing here, right? This is the means. So do as you would not, but I don't want to do that yet because I'm kind of keeping things simple. So first thing I'll do is just only go up to maybe 47 hertz. I'm not going to have our mains thing in there. And now we've got so some strong low frequency stuff. Altitude bumps. But what we often want to do is kind of bring out the smaller bumps. These kind of drowned out by large things like that, and that's what logging on the Y is helpful for. It kind of makes it so that you don't have any peaks or amplitudes that are drowning out everything else. So what we see is something that is kind of familiar. We've seen it in a few ways. There is an axis over. Maybe I'll just make the figure bigger. That would be a simple way of doing that. Yeah, no, maybe just a tad smaller than that. I'll zoom out a second. We have this 1F tendency, which actually more kind of clearly in the with the log decks, but like higher amplitudes in the low frequencies, and lower amplitudes in the higher frequencies. We have these peaks around here. These peaks are probably, I mean, this is a very short recording, so that's why this is so kind of noisy, right? If I'd have recorded for 5 minutes, this would be a lot smoother. But the lump here, of my actual alpha, the left-hand side of the 1/f, and maybe some low frequency artifacts from those jaw clenches and things that I was doing. But yeah, like some high amplitude around alpha. We have these peaks in the kind of 30 to 40 hertz range. These are probably generated by my jaw clenches. One way we could look at some of those things, especially if we did a longer recording, is to look at the power spectrum for a clean bit and a jaw clenchy bit and a blinky bit, for example. One or two other things. So here on the purple is not brain activity. The purple is a noise channel, but we're kind of just plotting it for a kind of comparison. Some strong harmonics in there. That would be the bass frequency is this one. So which is curiously, it's kind of in the brain power range, but the auxiliary channel is not recording any brain data. And like some other interesting things in here, some differences between the channels in terms of their profile in these frequency ranges. The final thing as I wrap up is just to kind of point to something that I was doing before, because we're mainly talking about loading and stuff, not so much analysis interpretation in here, right? But what I had at the top there was this function that I have used before for loading in those other files that you saw in the folder that I've kind of played around with and loaded in various points. And one of the things that this does, it does a lot of the stuff that you saw initially, which is like reading in and kind of getting the channel names. But then I'm putting stuff into an M&E object and returning that, returning an M&E object that kind of knows something about the montage in terms of the channel names and the channel positions, and so the kind of useful things that M&E objects come with, that it's worth incorporating into those objects when you pull your data out. So I have a function that just gives me that from the raw data, and I have another function that does the first set of things that we talked about, actually load into raw. Am I calling load into raw up here? No, I'm doing two. So these are two kind of parallel functions, but unzipping, reading into pandas, doing some organizing, again, loading into M&E and pulling it back. So this would be how I would normally do this, is have a function that kind of defines those things that we just saw, and then pull the data in kind of a one-liner through this function, and then start playing around with it from there. Okay, any questions on any of this?
That was great, John. Could we look at the plot one more sec for the? You had the different electrode power at the bottom, and I just wanted to point out that's a very clear illustration of the effects of that reference electrode in the front. And you can see that the signal levels are higher across the board for the rear electrodes. So TP9, the blue line, is the left rear. TP10, the red line, is the right rear. And you'll note that their power is significantly higher than AF7 and AF8, and that's the effects of that reference electrode. So still wonderful, but just be aware that there's going to be this power imbalance because of that design.
Do you want to spell that out a little bit more? How the reference is being
used? It was right before you joined, but I'm happy to cover it again. So it gets subtracted out from the electrodes, and the reference is right in the middle of AF7 and AF8. So the signal that it's recording is very similar to the signal that AF7 and 8 gets. So it cancels out a lot more of it. You tell me if that's correct, John.
Yeah, no, that's right. I just thought it'd be good for.
Yes. And TP9 and 10 are on the other side of your head. So they have a different enough signal. They're also sampling a different part of the brain, the temporal lobe instead of the frontal. And that means that much less of their signal gets subtracted by that reference, which means much more of the signal persists. So in this very weird way, you would think that blinks come through much stronger on the fronts because it's right there and you're moving your muscles. Nope. Because of the Muse design, you're going to see blinks really clearly in the rear electrodes.
Well, because it's referenced out.
Yeah, it's kind of wild.
Right.
Yeah.
Interesting.
And you'll still see blinks and eye movements and all that, but the amplitude of them tends to be a lot lower. One more thing that I'm excited to show you. next week, hopefully, when we're looking at some data, is you can actually classify eye movements by looking at the raw plots. I don't think we had a lot of time to look at that last time, but with the Muse, blinks look a certain way, jaw clenches look a certain way, but if you look up, there's going to be a particular set of artifacts that appear, and if you look down, one of them will be reversed. So it's actually pretty cool. You can make a little mapping of which way your eyes are moving.
Yeah.
With the Muse, yeah. Yeah, I thought it was pretty cool.
Yeah, we should do that next time.
Yeah, absolutely. Thank you so much. Do you want to struggle through the Muse LSL for a minute, or do you want to declare victory?
Maybe, but can I take a? It's not exactly a break, but I'm in the middle of reinstalling Muse LSL.
Sure.
So let's see if that works.
Yeah, no.
And maybe I can jump back on.
On my system, my horrible syntax. I mean, in the sense of, if I'm replicating a user having an error, maybe you can help me troubleshoot it.
Yeah, we could do that. Sure.
Okay, cool.
I'll stop my screen share now. If I can learn how to do that.
Okay, so here's my embarrassing error. And this, obviously we have the Blue Muse stream is still running. By the way, you can see that this is pretty stable because I've had this going the whole hack night and it's still good. So graphical corruption, we're pretending that's not happening. That's Windows 10 feature because Microsoft really wants you to use their game overlay. And yeah, but we've got it. I put it on my head now, so it's not just sitting there collecting ambient. And this was the syntax I was going with.
Just some kind of fun. Do you need to give it a full file path? Have you tried that?
I could try, yeah.
Maybe, yeah.
What would we do without you, John? Yes, okay, so when you're using Muse LSL, you must use the full explicit path, and that's something I totally knew.
It's not something you'd necessarily expect. It does seem like a bit of a unreasonable expectation.
No, it's good. It's good to know what to expect. All right. So,
but you also probably want to do D as well for duration.
Right.
I guess I gave you a default there, but if you do -D, then you could say 10. Right.
Okay, I'm going to be quiet for 30 seconds. I know it's a blessing.
All right, we need to come up with some conversation while Alex is being quiet. Put my foot in it saying that because I can't just leave it quiet for that long. What's going on here? So Muse LSL is it's as you can see from the screen printout there, it's doing two things: looking for an EEG stream and looking for a markers stream. Now, the markers stream is another thing that you would put on a kind of separate LSL stream that Muse LSL will, in a kind of smart way, know about and pull in while it's also pulling in the EEG data. So the way, as Alex has said, he's got Blue Muse running in the background. So that's streaming the Muse data on an LSL stream. What you could do, and what we do with EEG notebooks, and is put other information on another LSL stream, which is like a tags for events. But then Muse LSL will pull those in and integrate them into the same file. So you'll see that appear as a final column. And I think it will say marker 0 for this one that Alex just did, because there aren't any markers, but they would come in as like additional columns for every marker stream that you have. Okay, so you don't have, so if you had a marker, then you would have another column there for saying marker 0, marker 1, marker 2.
Yes, absolutely. And you can see that this is pretty much the same stuff that we got. It's the exact same formatting. So when you use LSL, you get the data structured the same way. So yes, these are two completely different apps, right? Where one is like a Windows specific thing that we wrote for our purposes. One is the software that Mr. Barashant awesomely wrote years ago, and we have leveraged ever since. But you can see it's identical. The order of the columns is the same. The electrode montage is the same, and somehow Muse LSL will insert timestamps, but I think the column is actually called LSL timestamp. So the neat thing about using LSL as a transport layer is if you subscribe to it, you get the data structured in the same way. And another thing that I think is really awesome about LSL, and I can actually show you this because we store this, is there's XML data on each stream that gives you the characteristics of what you're looking at. So if you use the XDF format, this will get saved. And if you query it through some code that you have, you can inspect this. But here is the stream information that LSL will send when it's transmitting. So there's going to be a device name. There's going to be a device type. So this is kind of cool. If you want to write an app that only subscribes to EEG or whatever, you can do that. It's going to tell you how many channels. It's going to tell you the rate. And then there's going to be a format for the data. So in this case, it's 32-bit floating point. And then you're going to get the labels for the channels. What is it? What unit is it in? And what type is it?
Great. And how do you pull that, Alex?
It's hard to get through Muse LSL because they abstract it, but this info is in the LSL stream characteristics. It's one of the things that you get when you connect to a stream. So if you have liblsl loaded in Python, and Python script, just like you were doing in Google Colab, you can, I don't remember the syntax offhand, but you can get it to spit out exactly this for any connected stream. Yeah,
it should be accessible through the LSL object.
Yes.
But not the command line interface, yeah.
Yeah.
Cool.
So this is just a handy way to kind of track the characteristics. So I just wanted to show you that data exists. I mean, Muse LSL doesn't make it easy to get at it, but if you want it, it's there. You just have to write some code to access it. But yeah, that's what's cool about using LSL is you get a level of consistency where as long as the interface sending to the device is the same, unless you've done something to change the data, you're going to get the same thing. Now, the last thing is, okay, so this was less noisy. And again, we see that the voltage ranges are what we expect. So if we do a quick and dirty plot, great. You can see how much more like EEG this looks like. We still have some spikes. Here's a blink. Okay. Because this data is so much more quiet, we can see it. So it's within a 50 volts oscillation range, which is what we want to see. And then right here, we have a blink. And let's say this is sample 613. So I'm going to get rid of this plot, and I'm just going to plot a smaller range so that we can see it. So let's just scroll down to 700 and just plot that for, sorry. Couldn't be doing this worse. Let's go TP9 to the start. Yeah. All right. Kablamo. Now we get this beautiful blink artifact. So here's what's cool about blinks. You can find them pretty easily in your data. This is what they look like on the rear electrodes where they come through real clear. So there is a big voltage dip So if you want like a really, really lazy way to find blinks, or easy way sounds so much better than lazy. Look for sudden drops outside of your voltage range. If everything is range bound to 50 microvolts and you're spiking minus 100 within a few samples, that's a blink, or it's an artifact that you don't want. So, you know, there's various ways to trim this out of your data, but recognizing a blink, it looks like this. It's bottoming out, a rebound above the baseline level. So this recovery always takes it higher, right? 50 is my range, but now I'm at 100 microvolts above, and then I return, then I recover. So all the data in this period is useless, you know, which sounds harsh, but unfortunately that blink artifact is drowning out whatever you're seeing, and it creates a very distorted, very specific power spectrum plot, which is going to be super heavy on the low frequency and the delta. So if you have blink artifacts in your data when you're doing your analysis, all it does is mess up your power spectrum. And there's all kinds of methods to remove them, M&E, component analysis, filtering. We'll definitely cover some of those things. But because this is such a short recording, here we go. Here's a real live blink in the wild. Okay.
So do you use that information, Alex, specifically in your analyses, like that profile of a blink artifact? You kind of have smarter algorithms that are informed about that, or is that just an observation?
Mm-hmm. Yeah, and we found a pretty cool way to trim them out to where, you know, it's really non-destructive. So it's been it's the clarity with which blinks come through on the Muse rear electrodes kind of motivated. But yeah, you know, I'm not sure how sensitive, you know, the things that you're doing, you know, maybe the windows, but since we're doing long continuous recordings, blink artifacts were a complete disaster for our ability to kind of like plot the PSDs.
Mm-hmm.
And I mean, you can try interpolating the data, you can try whatever, but honestly, after testing every single permutation we could find, zero padding is sort of the best way to handle it. Not concatenating, not interpolating, not doing anything else, but zero out your blink samples, and it's the least destructive to your data and leaves the original ratios of everything that existed. So that, I mean, you're welcome to do your own testing. You can focus on the blink artifact, you can plot it, you can do all kinds of other stuff. But we tried every single configuration, and zeroing out the samples during the blink works the best as long as you know, have decent sized windows that aren't just going to be all zeros. Do you have any particular method for trimming out blinks, John, or do you just kind of live with them?
I don't have anything special for this type of EEG system. In larger systems, you can where you have an EOG channels,
right?
Then you can do a lot. You know, the standard thing to do is something like you might do an ICA to look for blink components that you can kind of identify with their top topographies, but you can also use the EOG to find blink locations, and also you can kind of use it as a covariate and regress blink signals out. Sure. But for Muse devices, no, don't have like a kind of blink specific analysis approach, but the variance threshold method should do the trick for that, I would say, anyway. And you know, your example is a good one.
Right. And so if another thing that you'll notice, and this is sort of, we spent so much time looking at blinks, but this blink is about 120 samples long, starts around 524 and ends at 637. And that is the typical length blink that you're going to see depending on the subject. Some people have faster blinks, some people have shorter blinks. But let's just say on the Muse EEG device, which samples at 256, you can expect that the full blink thing is going to be about a half second of data. So now you're wondering, okay, how often do people blink? Well, a typical blink rate is 20 blinks per minute, which is about a blink every 3 seconds. So if you get that there's a blink every 3 seconds and you get that the blink blinds you for a half second, that's why blinks are really, really, really dicey if you're using a Muse to kind of do any longer term recordings. So here's the easy example, right? And of course, this isn't how you'd really do it, but let's just go to 650 and kablamo. Let's, well, let's try to insert 0 on all of them. Yeah. Good Lord. All right. There's got to be a way to zero all these out, but I'm not doing it. So if you do that, you'll just get a flat, section. And again, voltage thresholds work well. You're just looking for this sudden excursion. And once you cross the low point of your data, you're in a blink. You can probably just back up a few samples because it's going to be the start of the blink. 3, 4, 5 samples is sufficient. If you wanted the world's simplest Muse deletion classifier, look for this threshold drop, delete out 100 samples, move on. That's it. Once this crosses below the lowest point, just delete the previous 5 and the next, 100, 110 samples, and you're good. Okay. So yeah, that's the other electrodes. Let's just verify AF8 is going to be awful as usual. Yep. So AF7 looks great. We have a few spikes. These are no bueno. The stuff in the oscillatory range that we're expecting is good. Spikes are artifacts. You can use z-scoring and standard deviation to trim those as well. We'll get into that next week. I'll show you some of the cleaning scripts that we use. But given how range-bound the Muse data and EEG data tends to be, when you find major variations from the range, they don't belong there. It's very easy to delete the sample, and that's non-destructive to your data. So again, the exact same concept as blinks, but you can do it with spikes. And here is TP10, which super nice and clean, catches the exact same blink that we saw on that one on the exact same samples. So that's a legit blink because, hey, both electrodes saw it. So there you go. There's recording kind of like, you're going to get this flat file with some columns. Jaden showed how to kind of code up the BrainFlow interface and look at it directly. John showed us how to use Google Colab to take the files that we sent from the Mind Monitor and take a look at it. And yeah, here's plain old Windows, Excel. If you have a Windows workstation, you can use this to just kind of like inspect some basic data, and super straightforward. When you're using Muse LSL, don't make noob mistakes like yours truly. Give it the full path and you'll be a happy camper. All right, well, I think that's it for the demo portion of today's stuff. Oh, sorry.
Do we have someone that can show OpenBCI, or are we going to wait till next week?
Yes, sadly, I don't have OpenBCI gear with me, and I don't think we have Richard today.
Yeah, then we can probably do that next week.
The method would be the same as for the Neurosity, though, because
yes, if you're using BrainFlow, yes. And do they have a recorder with their GUI or no?
I think they might.
Sorry about the camera.
I can't remember, but if they do, it's probably as simple as it would be a CSV that you could do like the same that John showed, or use BrainFlow and do the same as what Jaden showed. So yeah, it would be more that if the GUI does have a recording function, that could be useful. Because then, since you have real-time visualization, you can record and have someone looking at the visualization and start and stop the recording when they want it, so that they don't need to spend as much time cutting out blinks or certain types of data.
Right. Yes, when I was first experimenting with muses many years ago, getting my start in neuroscience, all my recordings had 30 seconds of noise because that's where I got up and turned off the device. So I just knew to cut the last 30 seconds because there was nothing good in there. Much like John used the jaw clenches to bookend his recordings.
Yeah. Do you think it would be cool if you could literally use the EEG signal to tell it when to start and stop? Like, because it can pick up blinks or jaw clenches. What if you wrote a script that was like, start recording 5 seconds after you blink 5 times or something? Which I think would be a really fun little script or something. Because you're using EEG to record EEG.
It's true. It's true. And I guess you could also, the newer devices, I mean, obviously the accelerometer and the gyroscope is pretty good, right? You could make like, you nod 3 times and it'll start recording. But the PPG too, it's sweet. So I think I've seen some pretty cool Unity demos that use things like blinks and jaw clenches to navigate around. So it's pretty cool.
And SSVP is kind of coming in it to its own. I'm waiting till base Unity has SSVP in its input controller just as a normal option.
Right.
I would be so happy if like you can add EG device as Steam controller and then control any game using like SSVP on certain objects.
Yeah. I have to say I'm still super hot on eye tracking. Just the responsiveness and accuracy and all that stuff. I mean, SSVP is awesome, but I am so into eye trackers for sort of gaze awareness, if that makes sense.
Yeah. Eye tracking, I think both, so you have a redundancy, can be useful, but eye trackers are much faster.
Yeah.
At selecting stuff. But like, if you like, I'm pretty sure once you get down to being able to select stuff in under like 1/10 of a second, like 100 milliseconds, it could be pretty useful as a controller. Which
I agree.
A lot of eye trackers kind of limit you right now. They have the little like loading circle to select things. So I think with Toby, you could of course write your own stuff. Yeah.
So I think that this has been a pretty handy, like we've really covered the basics, and I know it's a little bit, you're storing stuff in the CSV and you're looking at columns and, the raw transformations. We haven't gotten to the good stuff yet, but I think starting next week is going to be the really fun, interesting contrast that we can do. So what we're going to be putting together for next week is getting together some baselines. so that we can kind of compare various things. We're going to be doing the experiment the week after that, but the baseline and interpreting them is a really, really good thing I think that we can focus on. So, I'm thinking, I found some interesting contrast based on the task. Like if I'm resting versus watching a YouTube video versus playing a driving game versus reading, they all seem to generate different oscillatory activity in the EEG, different spikes in the power spectrum. So I think it'd be neat, depending on what we can put together, but just get a few short recordings, 2-3 minutes of people doing various things and see, are we seeing consistency? What is the difference between the Neurosity data, the Muse with the Muse Mind Monitor, the Muse with the Muse LSL, and how exactly we go and interpret it. Like, how do you know that these are different, right? We've been looking at raw, which is not super exciting, but I think the fun stuff, the power spectrums, the band power, and the contrast should start next week. So, all right, cool. Thank you all for joining us. I think that kind of concludes this week's of, hey, you've got the data, you've got it stored, you can now visually inspect it. It looks about right. And that means that the frequency analysis can start, which is going to be the cool stuff for next week. So I'm going to go ahead and cut off the recording. All right.